Well, thank you very much for coming today. 10 o'clock on a Thursday morning. Clearly a fairly heavy night last night, but we'll carry on regardless anyway. Okay. My name's Chris Chisman. I'm Technical Director at TEV Limited. We have a couple of brands, which is Master and Quartz, manufacturing air conditioning and refrigeration equipment. And if you'd like to see us afterwards, we are based in Hall 6, stand 117. Okay. So in terms of what I'm going to talk to you today, the bit about the F-gas regulations has probably been done to death, so that's going to be really, really brief, but just gives a bit of context. Then we're going to talk about the product application of CO2 air conditioning, which is what I'm going to talk about today, about how it's applied. And then just to have a quick look at our products in terms of how they're used for CO2 air conditioning, and how to apply them and what they do. Okay, so briefly on the F-gas regulation. So we've probably seen this graph or a similar graph a million times before of what the original F-gas phase down was and what the new F-gas phase down is. And basically, there's a very, very sharp phase down. So in terms of if you're still using the old A1 refrigerants, there needs to be a move either to start thinking about either the A2Ls or CO2 or some sort of alternative. Because looking at the price trend graph back in 2017, obviously there was a big spike when there was a shortage of quota. Everybody at that point moved away from 404 and kind of rolled into either 448, 449, or there was quite a bit of movement to CO2 as well. And now we're back kind of into the spike phase where clearly I think there's going to be another rollover and a change very quickly, or at least the use of 448, 449 is going to become pretty extinct fairly soon, I believe. Okay. So in terms of what I'm talking about, it's air conditioning and heat recovery on CO2. Our cassettes are mostly used with packs for supermarket applications. And generally at the moment, if you're in terms of a direct comparison, if you're just doing direct with sort of normal A1 refrigerants or A2L refrigerants, relative to using CO2, you tend to find that it's more expensive, just purely because of the pressures that you're working with and the cost of the kit and just how complicated it is. So if you can do something in terms of improving the efficiency of the system, and by that I mean recovering the heat for air conditioning or doing a complete, doing the air conditioning and the refrigeration all in the one system, then you can do a lot in terms of making the CO2 much more sort of cost efficient, as it were. Okay. So now I'm going to talk a little bit about the application of the heating side. So it's pretty easy, really. In terms of how you apply, you'll have a pack system, and what you do is you take the gas off the main empty discharge line off the compressors. Normally you have a diverting valve, and you would divert the hot gas away, prior to the gas cooler, the main gas cooler, and put it through the heating cassettes. And that way you recover the heat. Now, there's a bit in terms of how you apply it is a little bit more complicated, which I'll come into a bit. But in terms of the actual physical setup, they generally sort of applied like this on the heating side. So on the cooling side, they're kind of similar to how you do the medium temperature cabinets. You have the receiver, which is like the intermediate pressure receiver. They're normally after liquid dryer. You would split off towards the ceiling cassettes, and then the gas from the ceiling cassettes would then go back to the MT compressor. The receiver normally on the intermediate pressure is around about 0 on CO2 systems, and that's about right for air conditioning. You don't want to be evaporating too low for any kind of air conditioning system. If you evaporate way too low, what happens is that you do a lot of latent duty instead of sensible duty. And what I mean by that is you're creating a lot of condensate and drying the air out, but not doing a lot of actual temperature cooling. So you want to try and keep the evaporating temperature off the system, going into the cassettes for cooling, around about 0 if you can. And that way you're getting the best in terms of sensible cooling and not just drying the air out and becoming some sort of dehumidifier. Okay. So next, in terms of the application on the cooling side, there's a typical kind of transcritical and subcritical graph. Obviously, we have the critical point, which is 31 degrees for CO2, 73.8 bar. Above that, you're in this sort of supercritical zone. But for cooling, everything is sort of on the subcritical side. So the way you apply it is very, very similar to the way you would apply kind of, I don't know, evaporators for cold rooms or something like that in terms of the way you size them. Generally, you need the evaporating temperature you're going to aim for, which, like I say, is normally about 0. The air on temperature that you're, possibly within the store or whatever you're doing, and then the airflow that you need. So applied in a very, very similar way that you would do, say, a cold room evaporator. On the heating side, it's more complicated, though, because there's kind of two systems that you may get, because you're now in the sort of supercritical region. So if you're transcritical, you need a lot more information. So as well as the airflow and the inlet temperature that we needed on the cooling side, we also need the pressure of the refrigerant, because that's the amount of refrigerant that's kind of in the pipes relative to the pressure. We also have the inlet temperature and the outlet temperature of the gas. So in terms of if you're doing heat exchange, it's generally this kind of temperature difference between the air and the temperature of the fluid within the heat exchanger that's important. So you have more parameters and more variables that are involved in terms of the transcritical region. If the CO2 is allowed to go subcritical, then actually it's very much like a condenser. So if you're sizing a condenser for a refrigeration unit, then similarly you just have the airflow and you just work with the condensing temperature against the external air inlet. So it's very similar. You have your delta T that you'd size a condenser to relative to airflow, and you just do that, but on the air conditioning side internally. And that's how you generally would size the heating if you're subcritical. Now, the next graph, we'll just go on to the next page. There is a big difference in terms of when you run the system transcritical and subcritical. So I'll just do a little explanation of this graph. So at the side, we've got the temperature of the CO2 fluid. This is for heating. And along the x-axis will be time. So if you imagine you are like the actual CO2 refrigerant traveling through the heat exchanger, when you're transcritical, the refrigerant almost behaves like a chilled water system, almost, really. What you're doing is the refrigerant is starting at a particular temperature, it's traveling through the heat exchanger, and then it's, because you've got a higher delta T at the beginning, you get a little bit of a curve as it cools down to your kind of off temperature. But what you'll see is the orange area of the graph is the amount of actual cooling duty that you're doing. So that would be like kilowatts in terms of the total area. Now, when you go subcritical, what happens is that a whole load of energy is required in terms of changing the gas into a liquid within the heat exchanger. So what happens is you lose a whole load of duty within the actual potential duty that the cassette can do. Running a CO2 system, obviously subcritically, is much more efficient for the overall system. But what will happen is within an air conditioning cassette, you actually lose a lot of duty. So when you're sizing a system up, you have to think about, because often when you need heating, it will probably be when the external ambient is at its coolest. So when you're sizing the system, you have to think about, will the system go subcritical, and how much duty will I achieve at that particular point? Because you can, to try and you may be able to artificially keep it transcritical, but is that really running the system as it's most efficient in terms of energy efficiency and what you're trying to achieve on the cooling side? Okay. So in terms of the products we have, so we do all sorts of types. So we do cassettes with 2 different types of fascia, as you can see on the top right there. We do ducted fan coils as well, again, suitable for CO2, which we have, live applications for. And we've also done wall-mounted units as well. Mainly in Scandinavia, we've done the wall-mounted. They tend to be less sort of recessed ceilings in Scandinavia, more solid ceilings. In terms of the heat exchanger types, within each unit we have the options. So we can do cooling only. So sometimes we've had options where people just want a 2-pipe system within the cassette, and they just want to cool because they might be doing like a food preparation area or something like that. So the unit just does cooling on its own. We also do types of units which are heating only. So quite often it might be that you have a small supermarket And what you want to do is recover the heat that you're getting from cooling your cabinets down, and you just basically directly pump that back into the cassette to obviously recover the heat that's available. We also, and these are probably the most popular, is we do 4-pipe units. So because within the system, your recovery, the actual system needs to be from 2 different places within the pack, you tend to have a 4-pipe if you want to do cooling and heating. So you have 2 separate heat exchangers within the cassette or the DXD. And that way, you can have, through the system, you can either decide whether you want to pump hot gas through it when you need heating, or you can do the cooling side and put some of the cold refrigerant through it if you want to do cooling through 2 completely separate circuits. We've also seen it where people will just want the CO2 cooling, but actually rather than running the hot gas through the store, what they'll do is they'll recover the heat into a plate heat exchanger and then just run the heat through an LPHW. So we do basically the different types through the various areas. And like I say, it tends to be for sort of comfort cooling, comfort heating on heat recovery. But we've also done some low temperature aircon as well, like I say, for food prep areas and that type of thing. So in terms of the types of products, what we've got here is this is a fascia for the cassette. Obviously, like I say, we've got various types that we'll have available. We can do different types if there is a requirement for enough, but we only stock certain numbers of the most popular ones. But we can design, if you've got a design where you think you're going to use something for a particular store rollout, then we can certainly design different types in terms of the amount of cooling and heating that you would have within the system. We also on here say that we have electric heating as an option, which is quite interesting. So you'd say, well, why would you bother with electric heating? Well, it comes back to the subcritical that we were talking about before, and where you don't get a lot of heat recovery. So in the morning, if you're doing a store or something similar, the cabinets are kind of cold, the room's cold, there's not a lot of cold for refrigeration. You want to heat the space, but there's no refrigeration happening, so there's no heat to recover. And if you try and do things like false loading or something like that, trying to run the system less efficiently, actually you're just adding cost to the system, quite a lot of cost, and really all you're doing is that you still need the same amount of cooling. You're just running the compressor inefficiently to add more energy to the system. And actually, from a losses point of view, you probably get a better efficiency level just by running an electric heater, get a bit of heat into the space, the fridge starts running, people can't come into the store, and then it's kind of becomes self-circulating from that point. So it's just something to give it an initial boost when you first go. In terms of each of the options that we have, on the cooling side, we work at 90 bar max working pressure. And on the heating bar side, we have 120 bar max working pressure. And also we can, if you want to, we can do pre-fitting of valves, depending on what type you want to go for on the cooling side. We also do the ducted type units as well. So yes, in terms of cooling, and we do options for those. At the moment with LPHW, we haven't done them with the hot gas heating, but we could. Again, it depends on what your application is. We manufacture in the UK, so we can design and build based on what your requirements are. Very similar, electric heating is an option. We also can do options in terms of return air plenums, different drain tray types for different valves. Again, it's all very bespoke to suit what you need. And finally, the wall-mounted units. These have mainly been used on cooling only at the moment. But again, if you have options in terms of what you want, in terms of heating, this is something we can definitely design for you because we've done it on lots of other units as well. So in terms of the business, to give you an idea, within the UK, we've won lots of awards for the various products that we've developed. So yes, if you find anything that you've seen today interesting and want to talk to us about our CO2, or want to talk to us about any of our A2L products, then come over to see us at Hall 6, stand 117. My name's Chris, I'll be there. You can talk to me or any one of my colleagues. Thank you very much.